Welcome to CPE 350, Chapter 8, Binary Mass Transport with Diffusion and Advection. This is example 17. We're continuing mass transfer in a falling film, and we're going to be non-dimensionalizing and solving the governing equation that we derived in the previous video. So the governing equation that we previously derived is given here, and the boundary conditions that we previously derived are also given. And what we see is that this governing equation is second order with respect to y and first order with respect to z. We've seen similar problems in this course, and the usual solution is to combine the y and z variables using a similarity variable, and that enables us to simplify the solution. So we're going to try that in this case, and to make that assumption, we have to get rid of our last boundary condition. Instead of requiring that the flux is zero at the liquid-solid interface, we're going to say that the liquid behaves as a semi-infinite material. And so at some point, infinity, there is absolutely no oxygen in the water. And so that concentration is zero. It's an approximation, but it enables us to solve the problem. So we choose a non-dimensional concentration and similarity variable in order to non-dimensionalize the problem. Gamma is our general constant for Gamma is the variable that we use for non-dimensionalizing concentration. And since there's only one concentration in the boundary conditions, Ca0, we just divide the concentration of A by the concentration Ca0. Then we can implicitly differentiate, and that's done. More challenging is to define the similarity variable eta, and we choose the second order derivative variable, which is y, and we're going to define eta as y over y star, where y star is some characteristic value of that length. This is a little bit trickier, so we need to derive an expression for y star that involves z and also has the units of length. And from previous experience, we know that we're going to want to incorporate the variables that we have in the problem, like the diffusivity. So in order to get the right units, we write the diffusivity over the velocity in the z direction, and then we have to multiply that by z because we need to incorporate the z variable into our similarity variable because it has to have both a y and a z to be valid. If you didn't expect this, that's fine. There's a little bit of play. There's no rule to how one defines a dimensional I would not have thought of this definition, and that's fine. There's no particular rule for how you have to define a dimensionless variable. You just need to make the units work, try it, and if the equation becomes non-dimensional and the boundary conditions can also become non-dimensional, then you've done the right thing. All right. And of course, because this has units of meters squared, we need to take the square root of this quantity to get the right units. So we've defined eta as y over the square root of 4 times the diffusivity constant times z divided by the velocity of z, and that's a function of y. The quantity 4 we've included the constant 4 from previous experience because we know that it will cancel out, enable us to more efficiently solve the problem. But if you didn't know that, that's fine. You would proceed with the problem, and eventually you'd work out that you needed an extra constant to make the problem more tractable. So now we need to implicitly differentiate eta with respect first to z and then with respect to y. So the differentiation with respect to z is a little bit trickier because z is in the denominator under a radical. So that's z to the negative 1/2. And so we get everything that's not related to z stays the same. Then we get a negative 1/2 because that's the power of z. And then we have to reduce a further power, so that becomes z to the negative 3/2. If we rewrite this expression, we can take a negative 1/2 power of z under the radical, and that gives us a negative power of z outside of the radical. So again, we've still got z to the negative 3/2. We've just reorganized the structure of the equation. And we recognize that that quantity is identical to eta. So actually, this derivative simplifies quite easily to negative eta over 2z. The derivative of eta with respect to y is a lot more facile to calculate because the derivative of y with respect the derivative with eta the derivative of eta with respect to y is quite simply 1 over the radical for dAbz over vz. So we've got our two definitions of the derivatives. Now we can non-dimensionalize the equation. And there's the governing equation. And so we start with the left-hand side, that second derivative of concentration with respect to y, and we can expand that as we've done previously using the chain rule. When we do that, we now need to plug in these derivatives we've previously calculated. And so if we make those substitutions, we get a simplified expression for the second derivative of concentration with respect to y. We can repeat the process for the derivative of concentration with respect to z. This is a little bit easier. We can plug in the expressions that we've derived previously, and when we do that, we get a much simplified expression for the right-hand side of the equation. Now we can put together the left-hand side of the equation and the right-hand side of the equation, not forgetting to add the constants dAb and Vz, and we get, with a bit of algebra here, the full governing differential equation using non-dimensional parameters. And now we have to start canceling things out and seeing if this is actually going to work as a non-dimensional equation. And so we do that, and in fact this simplifies quite readily to a non-dimensional equation. So the variables that we've chosen are fine for this process. Next, we need to non-dimensionalize the boundary conditions. So in real space, here's our boundary conditions, and it helps us if we rewrite the non-dimensional parameters that we've defined in the corner there. And now we can make ourselves a little table. And for the first boundary condition, at a z position of 0 and any value of y, we have that eta is infinity because anything over a denominator of 0 goes to infinity. And at the same time, gamma is 0 because the concentration of A is 0. So our first boundary condition, non-dimensional form, is that gamma of infinity equals 0. Next, we plug in that z can take any value, y has to be 0, and when we do that, y is in the numerator of eta, and so eta equals 0. At the same time, the concentration is Ca0, and so gamma equals 1. So that gives us our second boundary condition. Finally, for our last boundary condition, we have any value of z, and y equal to infinity gives us a concentration of 0. And so eta equals infinity, and we get gamma of infinity equals 0. Those two boundary conditions collapse, which means we've created a viable similarity variable and non-dimensionalized both the equation and the boundary conditions in an appropriate manner. So here's everything we need to work with: our governing equation and our two boundary conditions, because we've reduced the dimensionality of the problem from 3 orders of derivative to 2 by using a similarity variable. So to solve this, we substitute in a variable u equals the first derivative of gamma with respect to eta. And when we do that, we're able to separate and integrate this equation. So we do that separation, then we integrate, we get an expression in terms of natural log of u, and then we can solve for u. And I'm being a little rough with this variable c1. I'm calling it c1 prime so that we can say that the variable, when exponentiated, is equal to c1. So now we can replace u with d gamma d eta, our substitution, and then we have to separate and integrate one more time. So the left-hand side is straightforward, it's just gamma. The right-hand side, it looks like something you might be able to integrate manually, but it's not. It's a really wicked derivative. It's a really wicked integral. The solution is actually an error function. And of course, don't forget the constant of integration. So here's the solution to our governing differential equation. And now to actually do something useful with this, we need to remind ourselves of the definition of an error function. And so that is a normalized integral under the Gaussian curve. And instead of going from negative infinity to positive infinity, the integral is from 0 to x. When x tends towards infinity, the integral tends towards the value of 1. So with that definition in mind, we can rewrite our solution for gamma by multiplying by 1. So basically, root pi over 2 times 2 over root pi is the same as multiplying by 1. So we haven't changed anything. But we can factor out the first bit of this. We'll call that c1 double prime. And when we do that, we can take that outside of the integral. We've got our 2 root pi multiplying the integral, and all of a sudden we have an expression that looks exactly like the error function. So we plug in the error function, and that is the simplest form of the solution that we can actually use. To derive the particular solution, we need to apply the boundary conditions. And so we plug in for eta equals infinity, and we see that the error function of infinity goes to 1. And so we get that c1 has to have the opposite sign of c2. When we plug in the second boundary condition, the error function of 0 goes to 0, and we get that c2 is equal to 1. So plugging in these two constants of integration into our governing equation, we get the final solution, which is the solution to our concentration profile in the falling film. All right, thank you for listening so much, and I'll see you for the next video.